you can see in here that's where the maximum displacement is going to be. So let's go ahead and turn up that slider so you can visually, yeah, look at all that displacement there. All right, everybody. This is a failure analysis video on the jointed creek glider bait. If you watched my previous video, you'll be familiar with this clip where I cast one of these baits into a tree, pull it out with 20-pound braid, and the bait comes back and it's just the head section of the bait. And I said in that video, I wanted to do a failure analysis video on the lure to explain why I think the bait failed and why this isn't a design issue of that jointed section, but a manufacturing defect from when I put the bait together. So we're going to analyze the failure of the bait itself, the lure that actually broke. We are going to do some FEA and FreeCAD, look at the stress of that joint design, and then do a 5Y 8D problem solving methodology for our corrective action of how we're going to fix this in the bait moving forward. So let's get into analyzing the failure. You can see on the bait here, the joint broke in the middle section of the bait only. Zoom in here so you can get a better, but that area where the clamshell joins together, it broke only on one side, and that's where the wire pulled out from. If you look at the two end sections, nothing's wrong with those. The plastic didn't break there. So looking at the joint where how it is supposed to be, you can see we've got the two snap rings and the through wire that run through that bait. So when you're pulling on that tail section, that force is going to be transferred through these snap rings into the through wire, which is glued in on either end here and then UV resin coated over the whole bait. And if we look at this particular bait, it doesn't look like a whole lot of UV resin got into that joint where it was cured. And that could have contributed to the failure. So because of my engineering background, I already had a pretty good idea of the forces and the interactions that were at play that were causing that failure. And to kind of show that visually, I wanted to use the FEM workbench in FreeCAD so I can get a nice color map to show and explain some of the phenomenon at play that I believe are causing this issue. By no means is this going to be a video on how to run FEA in FreeCAD in the FEM workbench. I'm not that type of engineer to where I'm using this every day, but I am aware of it and how to generically use it to show some of the concepts that I wanted to show. So here I was just kind of playing with the areas, the faces that I was picking to load so I could show what I wanted to show. I was trying to make the through holes the constrained sections and the force applied at the nose of the bait. And that really wasn't showing what I wanted to show. So I'm going to skip ahead here and do a couple things and show some of the physics behind this. And eventually what I landed on was selecting the back faces of the joint as the fixed section of the joint, so that when the FEA ran, it would show where the stresses and forces would be in the bait where I would expect them. FEA is not a magic tool that will solve all your engineering problems. It's a tool that you have to understand the inputs and the outputs of and what you're really looking at, or else you won't get any valuable information out of it. And I think this loading condition is close enough to what's occurring in the real world that it'll show what's going on. Also, I was running this with a 20-pound load being pulled straight out from the nose of the bait as if the line was breaking, because I typically use 20-pound braid with this lure. But anyway, what you see here is the stress concentration is at the ends of the joint, the two sections at the ends, and not the middle section. In FEA, green is good, and as you zoom in there, the red and the green areas, or the red and the blue areas, I'm sorry, indicate the areas of the higher stress. So red being the highest, blue's a little bit higher. So that's where the strain in the bait, and where, if it's going to break under this loading, that's where it would break. And this loading condition is actually what I would want and expect in this type of bait. When I was designing it, what I wanted is that it would be distributed across the whole joint, as indicated by those red arrows in the middle area. And then flipping between the max stresses, the shear stress, max principal stress, the highest stress and the FEA that I saw was 38 megapascals for this load criteria. I would not trust that exact number, but what's going to be important later is how that number compares to the other load condition that I'm going to show. 38 megapascals being equivalent to roughly 5,500 psi. So what I wanted to do next was change the load condition to match what we saw in the actual broken bait, where it was just broken out at that middle section there, and then show what that would do to the FEA calculated max stress that we just looked at. Went ahead and reran that FEA analysis, which stands for finite element analysis. And as you can see, that max stress in that area is now concentrated in the middle joint, which is what you would expect. And if you look at the max stresses, it's 348 megapascals. I'm sorry, 346 megapascals. And if you remember before, the max loading was 38 megapascals, so it's almost a factor of 10, not quite a factor of 10, but almost a factor of 10 increase in the stress in the body in that particular area of the joint. The takeaway being that if all of the load of this bait, or most of the load, goes into that middle joint section, it's way more likely to break, especially in the manner which we saw it break. And just so you're aware, 346 MPa is about 50,000 psi. And to put that in context, the tensile strength of PLA, which is what this bait was printed in, is only about 7,000 psi. As with all things, there's a range to that. These baits are UV coated, and I use super glue to secure the joints better. But yeah, it doesn't really stand a chance against 50,000 psi. Then to further demonstrate this concept, I wanted to model up a mock-up of the through wire and show the interaction and the kind of the stresses that are occurring in the through wire itself under this particular load. So I mocked that up real quick, not real difficult, pretty easy in the part workbench. So I ran that through the FEA workbench, and the big takeaway here was the displacement, actually. When you looked at the stresses in the wire, it was some similar thing where it was off by a factor of 10, so I'm not going to show that. But when you look at the displacement of the wire, it's a pretty telling story. So this low condition is where it's only supported the um, at the ends of the bait and not in the middle section. And if you go through and do the little slider, and we're going to slide it to be a factor of 10 displacement, and you could see just how much of a bend that wire's taking on with when that middle section is not being supported. Now remember when we were looking at that break, where it broke out at, and then this shows a very telling story about why it broke the way that it did, especially when we compare it to the FEA that was run with that middle joint properly supported as our fixed bounds. So you could see very little deflection there. The actual deflection of the aluminum wire being 6 microns compared to 6 thousandths of an inch, which is what we saw in the last one. So here in the computer, we're able to show and match up with what happened in the real world here, where it broke out in the middle section, which tells us that that middle section was not being supported the way that it should have been, which means that the next question we have to answer is, why wasn't the bait in that section supported the way it was intended to be? Now I want you to imagine that you purchased this CAD file from my website and put one of these together and it broke like this, or you bought one of these lures off of me directly and it broke like this. You're going to be a dissatisfied customer. And in engineering, when you have a dissatisfied customer, they might come knocking on your email box and asking for an 8D. And what an 8D is at its core is a document that describes what the failure was, why it occurred, and what you're going to do to fix it. So one of the first steps of this method is defining what your problem is. And here, our problem is that the jointed creek glider broke in the middle section of the bait. In the first joint of the bait, more specifically. The next section for this video really isn't that important, but let's say I had 100 of these things out in the field, and I needed to determine where they went. That's where the containment section comes into play. So here it was only affected test samples, so not really much to say there. And of course we're going to be moving on to the next step. And here we get into the meat and potatoes of it, defining your root cause. This is the hardest part of the 8D. So here we're going to say the middle jointed section was not fully supported. That's based off of the break and the FEA analysis we did, where we could say, okay, that middle joint was not fully supported, and it looks like the through wire pulled out of that middle section because it deformed. That sounds like a reasonable root cause, right? So next we're going to go to our corrective action and we're going to say, okay, how are we going to fix that now? Alright, so corrective action comes directly from the root cause, and it feels like here maybe we didn't actually get to the root cause, because we can't pull corrective action right out from that root cause statement, which tells me we didn't go deep enough to identify what the root cause actually is. And to do that, we're going to use another tool called a 5Y sheet to really drill down and get to what the root cause of the problem actually is. So here we're going to redefine our problem statement, that the middle joint section of the through wire pulled out in that first joint, And then you're going to step through and keep on asking why these things are happening until you get it to a final root cause. Okay, so why did the joint pull out? Well, the middle joint section is not fully supported. Well, why isn't the middle joint section not fully supported? And then this is going to be the key piece of evidence in order to answer that question. So, this is a video short on my channel where I was actually making and recording myself making these baits. This short is still up on my channel. You can go find it if you want to, the full thing. But if you pay attention to the section where we're gluing the pieces together with the super glue and then inserting the through wires, you'll see where our problem is. Now, we put in the through wire with the split rings, and then we super glue just the end sections of the bait. We did not apply super glue to the middle jointed section of the bait. We're going to watch the video clip again. Put in the through wire with the snap rings on both sections of the bait. Apply the super glue just to the outside diameters, the outside rims and the hook hangers, not that middle joint. Now, ladies and gentlemen, we can go through and truly identify what our root cause is. The manufacturing process did not fully bond the through wire of the bait to the middle section. And this was actually something I thought was fine. I didn't think I needed to use super glue because I just assumed that the UV resin was going to hold up that joint and bond that wire to that area of the bait just fine. I didn't think I needed the super glue there. But then going through this problem solving methodology, we identify that wait, no, the UV resin isn't enough to bond that wire to that plastic. You need the super glue there. I thought I was just using the super glue to tack the wire and hold it in place while I did the UV resin, and that's really what was holding it in. Well, turns out no, it's not. Okay, so then why wasn't the UV resin bonding to the plastic well enough? Well, the UV resin, it's manually applied. I just dunk the whole lure in the bottle of the UV resin and then hold it up to a UV light by hand to cure it, and then wash off the excess resin. So it's a manual process, and I don't think it was getting into that joint as well as I thought it was. And then the next question is, well, why wasn't it getting and permeating into that joint like you thought it is? Well, I think the answer to that is that's just because of the geometry of the bait and how that joint is, and how you expose that UV resin to the light. The light's not going to get and permeate into that middle joint and cure the resin in there. It really can't. That's inherent to how the resin works. Okay, so now we've driven down and gotten down to our true root cause, and that the UV resin wasn't bonding the through wire to the middle section and supporting that joint the way I thought it was. And now I can come down and define what my corrective action is going to be. And it's going to be pretty simple. I'm going to start using super glue to bond the middle section joint to the wire. That's all I've got to do. I don't have to go back and redesign it. So now we can go back to our 8D, redefine what our root cause is, and then choose and implement our corrective action, which we said we're just going to start using super glue to bond the middle section joint to the through wire instead of relying on the UV resin. And now that we've identified what we're going to do to fix the problem, we can go ahead and implement our solution. So we're going to say that future lures, we're going to use the super glue in the middle. Well, it really should be in all the sections where we need to bond that wire to the plastic, instead of relying on the UV resin clear coat to do that bond. Because remember, it's not just important in this joint, it's important in the hook hangers and the lure eyes and anywhere else where that wire needs to be bonded to the plastic. We should be using super glue to bond it, not relying on the UV resin. And this next step really isn't applicable here because it's just me putting these together, but in industry, what you would want to do is rewrite your work instructions and train your operator to include what we just discovered as a critical step in the manufacturing process to make these baits the way we're supposed to. Alright, so we're made it. We made it through the problem solving. We've implemented our corrective action. We know what went wrong now, so now we can get back to making these beautiful creek gliders. I hope you guys enjoyed the video. If you want the CAD model for this bait, go ahead and check out my website, www.3dprintedmolds.com. Hope to see you there.